we're getting movement, linear movement, so moving forward by rotating about our joints. And that's why we're always going to have a component of both of these in anything we're doing. So if you think about throwing a baseball, we've got the linear movement of the pitcher going towards home plate, but then we have the angular movement at the shoulder, at the wrist, through the torso, and through the hips that are all going to combine to add to velocity to how effectively hard they're throwing that ball. So anytime something is effectively in flight, it is considered a projectile. Okay, so this is going to be a ball. This could be obviously something like a javelin. And if you are strong enough and or a cheerleader, this can be a human. And also, I believe the colloquial term for you guys using it is you can always yeet yourself. Please correct me if I'm incorrect on that assumption there. So the actual flight path of said object is going to be what's known as the trajectory. And this is where, with a great enough velocity over a great enough distance with a spin, and then also some features that are creating differences in air pressure on one side or the other, can cause that object to curve. So think about a wiffle ball, think about golf, where people can like slice the ball or otherwise, where it's going to take a hard turn. And this is going to be, once again, that trajectory. Now, the trajectories that we're going to work with, we're not going to worry about spin, but we're going to deal with what's effectively is basic projectile motion. So we're going to have to use those force vectors, and then we're going to have to use some wonderful mathematical formulas to effectively infer how far something would have flown, what's going to be the angle on it, so on and so forth. So how far something goes horizontally when we're talking about flying through the air is going to depend effectively on three different things. One, the angle of release. So did we throw it straight up where it's not going to go anywhere? Did we throw it flat? Good Lord, guys, to where it's going to not go that far, where we put an angle so that way we can get a little bit of lift. Effectively, it's going to have a vertical displacement up and then down, so it's going to spend more time in the air. Now, velocity, obviously, the faster it's going, faster the ground is going to cover it, and that flight time it's going to have, what goes up and comes down. And then, obviously, the height of the release. So if we were to be on campus with you guys, where could we get nearly any of you guys to be to where you could probably, probably throw a baseball in the air, 200 plus feet? Where could we put you guys to where you'd be able to throw a ball that far? Think about making it even easier than that, Ethan, where we can really take advantage of one of the three of these. I mean, the football field, you'll have the straight distance, same thing you'll have in the baseball field. Some of you guys might even be able to throw the ball 100 yards. Where would we want you guys to go? Yes, Zach. Top of Commonwealth. You got 20 plus stories for that ball to fall down. So as long as you give it a decent enough horizontal velocity to start, it's got a lot of time to fall back to the earth. So the angle of that release is going to determine its shape. Okay, so obviously if it's straight up and down, it's going to go straight up, straight back down. If it's above 45 degrees, there's a greater vertical force component compared to the horizontal. And if it's below 45 degrees, it's going to have a bigger horizontal component compared to the vertical. Now, like anything else, if it's at 45, it's got the same amount of vertical velocity as it's going to have horizontal velocity. Now, since we obviously live on Earth, not everything is going to go a max distance when it's released at 45 degrees. We've got things like wind resistance that are going to be factoring in. We've got aerodynamics. So for example, when a long jumper is trying to obviously jump as far as possible, their angle is only at about 20 to 22 degrees, okay? We're not all the way up at that 45, much less way higher beyond that. The simple reason for it, if they were to go at a higher release angle, they would effectively give up too much speed for that higher essential jump angle. So we still need to think about what's going to be the most optimal. And like anything else, when you start with throwing anything, we're starting above the ground. So we're from where we're released. So for me, it's going to be 5, maybe 6 feet off of the ground. And then the ball would then go and eventually hit the ground. So if I was throwing the shot put, it would be more like 5 feet off the ground. I'll release maybe at 6 feet. And from there, that angle of release, again, we don't want it to be too steep because we're going to be losing too much horizontal velocity in order so we can just have some vertical. And we're going to find shot, javelin, discus, even throwing a baseball or softball, we're going to find an optimal release angle given if we're going for maximal distance. Now, obviously, sports like baseball, sports like softball, basketball, we're not looking for maximal distance. We're looking for getting that object into or to a certain location as efficiently, as quickly as possible. So that's going to require, obviously, making sure that we're making those essential decisions in our head. So given how hard you're going to be able to throw that object, how fast will it go ahead and cover that distance? Is it going to get to where you want it to be in the brief enough time so you're going to be successful? So now remember, velocity is essentially the length and size of the trajectory. So that's literally just how fast the object is going. So the bigger the velocity, the greater the trajectory, the faster it's going to be obviously going initially, and the further it's going to go overall. So if you were to go ahead and let's just say take a baseball or an object and just barely throw it, it's probably only going to go about a feet or a couple feet, 3, 4. Now, if we go ahead and put a little effort into it, maybe now we're going 10, 20 miles an hour, and it's going to maybe go against the room or go to the other side of the room. Now, if we go ahead and just fire that as hard as we can with our entire body, we might be talking 50 to 80 miles an hour, depending on how good your throwing arm is. And that's going to probably go, well, since I'm doing this lecture from home, it's going to go into a wall in the house, and that's bad. And then if we were to mount a cannon and fire that object at 300 feet per second, it's going to not just go through the wall of my house, quite possibly going into the wall of my neighbor. And I'm going to have some very interesting conversations to have about why I'm launching baseballs using effectively what looks like a potato cannon. So faster it's going to be going, the further it's going to go. Now, all of this is to build up to allowing us to calculate. The higher that release, the more time it has to come back down to the ground. So hence why if we throw it from the top of a building, it's got a lot more time before it's going to go ahead and hit the ground, given then it's going to go ahead and travel even further. So what does this mean for an actual athlete? Well, it turns out, like anything else, it's going to help us make decisions as to what is effectively going to be the best technique. So you can imagine for a baseball pitcher, having them understand that angle of release and the height of the release and how that's going to influence the ball trying to go where effectively they're trying to locate it into the strike zone. For the javelin thrower, we're really looking at optimizing for distance. Now, for somebody like a free throw shooter, what are we going to be, if we think about the trajectory, think about the total angle, what does this help us inform when it comes to coaching a basketball player? Yes, Anna. So we want to have a higher angle of release for a free throw. If you throw it on a straight line, you're just going to hit the rim. It's never going to go through. You obviously want the ball to arch up and come back down into the basket. That requires, obviously, a steeper release angle. In fact, statistically speaking, if every single professional basketball player was to shoot it granny style, between the legs, they would actually make more free throws. But due to the joys of toxic masculinity and appeals to tradition, athletes seldom ever do that. And instead, they miss a lot of free throws that otherwise they could have made, which in turn would have allowed their team to win. But they wouldn't look as cool doing it. So if you're not going to look cool, what's the point of doing it, right? So this can help you think about what's going to be the most optimal technique for what you're trying to accomplish. So now we get to have some fun, which effectively is we're introducing the mathematical formulas that are going to be related for figuring out how far these objects went. So horizontal distance is going to be equal to, okay, x, and just so you guys can also see this here, x is going to be distance. V equals velocity. T equals time. And A equals acceleration. Okay? V sub O equals the initial velocity. So that's why you see horizontal velocity doesn't change. Whatever the initial horizontal velocity is, the same as the final horizontal velocity. However, the essential velocity formula, which then incorporates the potential of acceleration. And acceleration, remember guys, is what we are under the influence of from gravity at all times. It's constantly pulling us into the center of the earth. So we have to obviously choose to stand up and resist against that force. So given these formulas, we're just going to attempt to have a little fun. We're going to start off with the horizontal component, and then we're going to go ahead and start working into the vertical component, and then we're going to start getting wild with some actual flight information. So the first problem, yes, angle of the throw, Anna, is the angle of the release. Oh no, we already covered that. My apologies. Okay, so let's say, and we're going to, velocity is always going to be, let's just make sure that I say this, which is going to be in meters per second. Okay, distance is in meters. Time for what we do is going to be in seconds. And actually, yep. The joys of having fat fingers. Acceleration equals meters per second squared. Yeah. So first problem we're going to do, okay, if we happen to be on a bike that's going 5 meters per second, okay, and we ride on it for 10 seconds, how far have we gone? So this example, we're simply using the horizontal distance. Bingo, we've gone 50 meters. Okay, it's pretty straightforward, pretty easy, okay? But now, we're gonna go a little differently. We're gonna say the same situation, okay? We're on a bike, we ride it for going at 5 meters, sorry, per second. That is de-accelerating at 1 meter per second squared. We ride it for that same 10 seconds. How far have we gone? So now we have to use that third formula, the distance formula. Okay, Josh came up with 5. What else are you guys coming up with? You guys, don't be afraid to put your answer in to everyone. Well, that's a 0. So the answer, guys, overall is actually 0 meters. It'll literally, because it's deaccelerating, so it's slowing down, slowing down, slowing down until it hits 0, and then it's actually going to start going backwards, backwards, backwards. So it actually ends up overall traveling 0 meters. It literally stops where it started. So now, let me move this around so I can get to what I have posted in here. There is a y at the end because of the release angle. So if you had it negative or positive, you would have to change that appropriately. So now, folks, at the end of that exact example we just did, how fast is it going? How fast is it going? Nope. Yes, guys, -5 meters per second. So remember the good old Pemdas? So whenever we're doing any math, think of your order of operations, guys. So parentheses, exponents, multiplication, division, addition, subtraction. So we need to make sure that we do, in these examples, our multiplication before we do our addition or subtraction. And that's going to allow us to get the answers that we are looking for. So it's okay if this is a little muddy, guys. It's completely all right. So now what we've got next is going to be introducing some trigonometry. Yeah, okay, I left myself a note about this. I can go and delete it now. So, which is helping us figure out effectively what is the angle of our initial release. And from there, if we know that angle and we know the initial trajectory, we can figure out the vertical and the horizontal components for that velocity and then factor for both of them. Now, for all of your tests and quizzes, I suggest either printing this off yourself or keeping it up in the background. That's where you're going to see where it says equation slide. Before the sickness came, I would always have this up on the wall whenever the students were taking any of my quizzes or exams. This is effectively your cheat sheet of every single formula that we use in the class. So, you just need this and it'll take care of itself from there. And that all you have to do is obviously follow the information of whatever we're specifically working at. So effectively, so far, we have only covered through here. Now, the trigonometry is important because that's going to help us figure out, if we release at certain angles, how fast an object's going to be going, because we can break it into individual components. So let's go ahead. We're going to come back to the trig slide just for a moment, okay? And we're now going to say a ball, spacebar would be useful. So we're going to say a ball is thrown at a 30-degree angle. So what is going to be the vertical velocity and what is going to be the horizontal velocity? And this is where trigonometry comes in, okay? So what we have here when it comes to trigonometry, the long side of your triangle is always going to be the hypotenuse, okay? And that's what we know. We know the hypotenuse in this example is 10, okay? From there, the angle that it's being released from is going to be right over here. So if we can solve for what is known as the adjacent, so right next to the angle, that's going to give us our horizontal. The opposite is going to give us our vertical. So what we immediately have when it comes to the trig in this example is going to be the sine of 30 degrees equals, okay, the opposite, which we don't know, divided by the hypotenuse, which is 10. Okay, so what we're going to do from there is some cross multiply and divide. So if we multiply both sides by 10, okay, we're now going to have effectively a formula of 10 times the sine of 30 degrees equals our opposite. Okay. And that is giving us the vertical velocity. So we bring up our handy dandy calculator, which obviously feel free to use your phone and otherwise. But if we go trigonometry, well, let's go ahead and go here. Notice it says we're in degrees because we want that because we're working with degrees. Sine 30. Well, that did not work well. Let's try this one more time. Yay, the sine of 30 equals 0.5. So in this example, we're going to take 0.5 multiplied by 10. And yes, Kristen, great job. That gives us 5 meters per second. Okay. So then let's go ahead and solve for the horizontal velocity. So that's going to be equal to, now the cosine of 30, okay, equals the adjacent divided by, once again, the hypotenuse. So in this example, it's going to be 10. So this in turn will give us 10 times cosine of 30 equals the adjacent, which is going to be equal to horizontal velocity, equal to, great job, guys, great job, 8.66. So just so for you guys that are watching, go ahead and hit clear. We're going to go ahead and hit 30 again, trigonometry, cosine, and then that's why you get 0.866, and we multiply that by 10, so 8.66. You do not need all of these significant figures. That's a little ridiculous, but you guys at least have the method of seeing how this works. For those of you guys using cell phones, you might notice when you have the cell phone like up and down, you can't see the trig functions. If you turn it sideways, that's usually when the trig functions will show up. Otherwise, you know, a laptop should have it. You might have an old school calculator. You can even use Microsoft Excel. Just make sure that you're doing this in degrees, not in radians. If you're doing this in radians, because radians are equal to pi, things are going to get wild real fast, and it's not going to work too well. Okay. So we know how to find the vertical and the horizontal. Okay. So the next question we could do with this is effectively go and look at our horizontal distance and our vertical distance. So we could effectively go, okay, given this information, effectively after 2 seconds, how far would the ball have gone? So the horizontal is really easy. We just 8.66 times 2. So that's going to tell us that the ball would have gone a grand total of 17.72 meters. Cool. Now, whenever we go and now check out, or not check out, but look into effectively, sorry, 17.32, my bad, meters. Let's figure out the vertical side of it. So we have that initial velocity of 5. So 5 times t, which is going to be 2 in this example, it's going to be 10. Then it's going to be minus 1/2. Now, we haven't talked about before is gravity. Gravity for everything you do in this class is going to be 9.81 meters per second squared. So we take 1/2 of 9.81 squared, or sorry, 9.81 meters per second squared, multiplied by time squared, which is going to be 2. So 2 times 2 is 4, times 1/2 is now back to 2, multiplied by 9.81, which is going to give us 19.62. So since that's negative, that means after those 2 seconds, the ball would have actually gone a negative grand total of 9.82 meters. So that's kind of far. That's not kind of far. I mean, it's effectively almost pretty much 10 yards. So we're talking 30 feet down after just 2 seconds with given those velocities that we gave it. So instead, what we can then try and solve for is, okay, given that vertical velocity of 5 and the acceleration of 9.81, where or at what time would it hit the ground? So that's where our distance here for the y is going to be equal to 0. V sub o is going to be equal to 5. And then our acceleration, once we take the 9.81 multiplied by 1/2, is going to be equal to 4.905. So from there, we then have an a term because it's going to be to time squared. We have a b term, which is going to be that 5. And we have a c term, which is going to be 0. And we literally have to run it through the quadratic formula. So it'll give us 2 different times that it was on the ground. One is obviously the initial point where you threw it from, and the other would be forward in time. That's why you need the quadratic formula with projectile motion if we're trying to figure out the time at which it hit the ground. How are we doing, guys? Whose brains be melted? I can appreciate that. All right, so we're going to go ahead and we're going to have you guys work in groups, okay, and work your way through an example. So we obviously just had the ball that's thrown at 10 meters per second, okay? Yes, give me one moment and we will go ahead and go through the bike formula. So if we go to the third bike one. Yeah, so for this one, remember guys, we're gonna go ahead and plug in. We want the effective velocity. So the initial velocity here is going to be 5 plus or minus, and notice it's deaccelerating, so it'll be a -1 for acceleration times 10. So -1 times 10 is going to be -10. So 5 minus 10 is -5, so your velocity there would be 5 meters per second. So I'm going to give you guys, honestly, we'll give you guys 5-10 minutes because you're going to have to go through and do a decent amount of work to break all of this down. Okay, so I just put it up in the chat. We're going to put you guys, there's 21 of you today, so we're just going to put you in a group of 5 so you guys got bigger numbers to work with. First thing you guys are going to have to do is do the trig for effectively figuring out what is going to be the horizontal and the vertical velocities. Then you're actually not going to do how far it will travel before it hits the ground first. Instead, you would do it at what time will it hit the ground. And that's where you're going to go ahead and do your factoring and solve for effectively the vertical distance when using the quadratic formula. And then once you have that time, then you're going to be able to take that horizontal velocity, multiply by the time, and boom, you have the horizontal distance. So it's 10:06. I'm not going to have you guys, I'm not going to hit the close button until about effectively at least 10:11 to let you guys work through this together, and we'll see what answers you guys all came up with. So obviously talk with each other. It's okay to struggle, guys. Do your best and hopefully have a little bit of fun. All right, so give it some go. So,
I have a question.
yeah, what's up?
Where did you got the gravity from, like the 4.905?
Because we start off with gravity being set at 9.81. So then whenever you divide that in half in the actual distance formula, the third one down you see on this slide, that's going to give us 4.905. And then because of the quadratic formula, we just have to multiply it by 2.
Oh, okay, thank you.
Okay, no
May I
worries,
ask
guys.
a question too?
Yeah, what's going on?
Why is T 1 in this problem? It seems like it should be 0.
T is 0. Or no, sorry,
No.
it's not 1. T in this example is what we're trying to solve for. We don't know what T is. T has now, for the sake of this problem, it is now X. So that's why our A term is for what essentially acceleration is. It just happens to be a happy little coincidence that A in the quadratic formula is the same as acceleration. And then our initial velocity, that V sub O, that's our B term. And then our C term is where we started off of the ground. So we're trying to solve for time because, I mean, if any of you guys can look at that initial formula of, because we're trying to solve for the vertical distance of 0, where it hits the ground, equals your initial velocity, which was that 7.5 multiplied by time, and then it'll be minus 1/2 of 9.81 times time squared, minus 0. You can do that in your head just looking at it. Please go to the math department because they need your skills in higher level mathematics in this world, and your skills are being wasted here. But I definitely can't figure that out looking at it like that. Hence, we got to run the quadratic formula. But getting back to it, guys. So effectively, what we're going to have is, notice in one example, we're going to have negative 7.5 plus, because it knows it's plus or minus, 7.5. So we're going to have 0 over 9.81 equals 0. Makes sense. The ball starts on the ground. So then we have the second one, which is going to be negative 7.5 minus 7.5. So what we're going to have effectively is negative 15 over negative 9.81. So if we take that, and remember, a negative over a negative makes a positive. So what we're effectively going to have is 15 divided by 9.81, which is going to give us a grand total of a flight time of T equals about 1.53 seconds. And so if we knew it had a flight time of 1.53 seconds, now we go all the way back to our initial horizontal velocity, and we are going to, or sorry, yeah, which was 12.99, and multiply that by 1.53. And so we're going to have the total distance it's going to have gone, which turns out is going to be, relatively close to about 20 meters. All right, so question that Taylor has. In these problems, will A always be plus or minus 4.905? No. Because we might have examples of acceleration where we're on a different planet, because it entertains me. We might have examples where we're influencing acceleration in one way, shape, or another. So the key is And sorry, Marlana, I just realized you asked the same question. Acceleration, okay? We're going here because this is on Earth and using Earth acceleration. So 9.81 times 1/2. That's why we come up with a 4.905. If we were on the moon, where gravity is much lower, I couldn't tell you what the acceleration of gravity is there. That's just one Google search away, but it's probably something more like only like probably around in between 1 and 2 meters per second squared. So then you would multiply that by 1/2. And then that would give you effectively your A term, but more importantly, would give you essentially the effects of acceleration. Okay. So working through this together for the second half of the problem, because I know obviously I didn't give you guys enough time, so I'm going to give you guys some more time on this next one. Is that making a bit more sense? Okay. Okay, so now we're going to give you guys a slight difference or different problem, which is a ball's thrown at 20 meters per second at a 45-degree angle. So it's going to have that equal of vertical and horizontal velocities. Same question. How far will it go before it hits the ground, and how long will it take for it to hit the ground? So good news is you only got to effectively, because sine of 45 and cosine of 45 is the same, it's 0.702. But then after that, you're going to have to work through the math, work through that quadratic equation together, guys, and let me know what you come up with. So copy down, literally, so like select the text that I put in there, copy it, so you guys are going to be able to paste it back into those breakout rooms. We're going to use the same breakout rooms that we did before, okay? And like I said, like you guys just did, give it your best, think your way through it. If you have questions, comments, concerns, do your best to work through it. I'm going to give you guys, it's 10:24, plan on 10:34 is when we're going to come back in. So you guys got 10 full minutes to work together on this. So go ahead, good luck, work together, guys. Don't just do it in silence. Let people know what you're doing and ask questions if you're being held up, okay? Whenever you guys are ready, go ahead and paste in your answers for each part of those questions. So what is the vertical and the horizontal velocity, which should be the same number? What would have been, yes, absolutely, Taylor. Good work there. Okay, Sam, you guys are not that far off, but both your distance and your time to hit the ground looks a bit small. Anna, that looks right for the flight time. 2.88, 2.87, just like anything else with rounding. That could obviously have been a bit different. And are you sure about that horizontal distance? Because if it's 14.14 meters per second and you multiply that by 2.88, even if you multiply 14.14 by 3, that's only going to give you 28.42 and some change. So you're a bit over on your horizontal distance, Austin. Dakota, good job. And Zach, that's pretty much what I came up with for the horizontal distance, just a little bit off, but that's more rounding. That's okay, Anouk. Okay, guys. Not bad. Obviously, like anything else, this is new for you guys. You haven't done this before, so, you know, we learn by doing. So getting a chance for you guys to work in groups and try to figure out what the solutions are going to be. So effectively, you know, this is what I wanted to expose you guys to. We're going to work through some more problems of this on Thursday, along with, yeah. So what you're going to do is, yeah, for horizontal distance, guys, all you have to do is literally run this formula. You just take that horizontal velocity you had of 14.14 and multiply that by 2.88. Oh, fascinating, Kristen. This should be chapter 2 in the text. Leverage is getting more into chapter 4. So that's fascinating. And it's okay, guys. I have another lecture up there that you guys can look at, which will probably help. And it's okay, Austin. You should be able to find the one where I talk about thinking in units. So it's kind of how to think as we convert from one unit to the other, because we're about to go into a lot more units when we're getting to chapter 3, maybe a little bit on Thursday if no one has questions, but definitely next week. I got the 2.88 seconds whenever I ran that 14.14 vertical velocity with a term, remember like we did before, the quadratic formula of 4.905 and then an intercept of 0. So it ends up with, in the quadratic formula here, guys, your B term is that effective velocity part of the distance formula. So that's going to be that 14.14. Your A term is going to be the 1/2 times the 9.81, so 4.905, and then factoring through the rest of it. So effectively, your final quadratic formula should, I'm going to go ahead and figure out what's going on with the chapter numbering in the books, guys. Are you sure you're looking in the right book, since there's 2 separate ones for the class? But I will double check on that after we get done lecturing today. Where, fascinating. That's on me. I'm gonna work on that. So your B term should be that you should be left with essentially negative 14.14 plus or minus the square root of 14.14 squared minus 4 times 4.905 times 0. So that just gets scratched out. So you end up with a final equation of negative 14.14 plus or minus 14.14 over, since it's 2 times the 4.905, that's negative, you're going to be with negative 9.81. And so that in turn is going to go ahead, one of them is going to be a 0 because we started at 0. So negative 14.14 plus 14.14 equals 0. Then you're going to do the flip side of it. So you're going to get negative 28.28 divided by 9.81, and that's where you end up with the 2.88 seconds. So a lot of stuff going on there, guys. A lot of stuff. So questions, comments, concerns, because I know we just kind of did a little brain stretching today, and we're going to come back and try to look at it from the other direction, where we're going to know how far something traveled in a certain period of time, and then figure out what would have been its initial velocity and what would have been its release angle. Anything else you guys want me to work through or talk about before we call it a break for the day? All right, well, good work today, guys. Nice work showing up. If you have questions, comments, concerns, please shoot me an email. Stay safe out there and have a great day, guys. All right, bye-bye.